upcoming experiment in Chem 1212 involves the synthesis and redox titration of a transition metal oxalate coordination compound. And so in the first part of the experiment, you're going to choose one of three transition metal oxalates to synthesize involving either copper, iron, or cobalt. And then in the second half of the experiment, you're going to, first of all, standardize a solution of potassium permanganate. You're going to create that solution and then standardize it, and then use that solution to titrate the oxalate inside the metal oxalate compound that you synthesize. So the goal here is to first make the compound, get a sense of the percent yield, and then assess its purity doing a redox titration with potassium permanganate. So in this video, we'll talk about the theoretical background of redox titration, which is similar operationally to acid-base titration, but distinct in the type of reaction upon which the titration is based. We'll also talk more generally about coordination compounds, coordination complexes, what they're made of, how we think about them, and what they're applied for. Let's begin with a general introduction to the idea of a coordination compound. A coordination compound is defined as a compound containing a coordination complex, which is a complex of a metal M with ligands L, often, although not always, with charge. So here I'm representing the coordination complex as Ml sub n for n ligands, n ligand molecules, with a net charge of A+. Now the compound as a whole is neutral by definition, and so there are some number of ions X, say 1X with a charge of A-, to counterbalance the charge on the complex, if any. Coordination compounds are made through the union of a metal salt and often a salt of the ligand or the neutral ligand itself. And so we can think of, for example, Ma plus Xa- as a metal salt combining with N moles per mole of Mx of the ligand to form MlNX, the coordination compound. And in this reaction, we think about it in terms of the Lewis acid-base model. Ma plus is acting as a Lewis acid, or electron acceptor, while the N ligands, each of which typically contains a non-bonding lone pair, or at bare minimum, a pair of electrons that can be donated, that this means that the ligand is serving as a Lewis base. Now, Xa- is there as a counterion just to ensure neutrality on everything, and it's referred to as a counterion because it counters the positive charge of the metal ion Ma+. As I alluded to earlier, the piece of the coordination compound that actually contains the metal ligand bonds is known as the complex, or the coordination complex. And this is where things really get interesting in coordination compounds. This is typically where the business occurs and where we have interesting types of bonding, because of course the bonding between the complex and the counterion is just a simple ionic bond. And if we dig into the metal ligand bonds in coordination complexes, we observe something somewhat interesting. The bonds are made, quote unquote, through the donation of two electrons from the Lewis basic ligand, which is acting as an electron donor, to the Lewis acidic metal cation Ma+, which is acting as an electron acceptor. This is different from sharing in a covalent bond between two nonmetals, where the sharing is equal or somewhat polarized. Here, we could argue there's extreme polarization, with most of the electron density on L and very little on M. But there's still covalent character to this bond, and so it falls somewhere in this murky area between covalent and ionic bonds. And in fact, it's really in a class of its own. These are called coordinate, covalent, or dative bonds. And they're often drawn with arrows like this from the Lewis base to the Lewis acid, although you'll also see them drawn with solid lines in many cases. Before we get into the details of this experiment, I did want to briefly talk about the applications of coordination compounds, and two in particular where they're very commonly used. The first is in catalysis. Metal complexes, particularly those with positive charge, are often Lewis acidic, and these can be used to catalyze transformations. So say we have a reaction A goes to B, the inclusion of a coordination complex can often accelerate reactions. And so these are commonly used as catalysts. They're also applied in analytical chemistry because there are often very well-studied, easy to apply analytical methods to quantify the amount of a coordination complex. In fact, we'll apply one in this experiment. So say, for example, I've got a metal cation M2+ that I want to quantify. I've got some environmental sample. Maybe I'm looking for iron 2+. Well, I can complex iron with some ligand to form a coordination complex that is very well known, the properties of which are very well known, and then I can quantify that complex using, for example, spectroscopy, titration, or some other analytical method. So say, for example, The complex absorbs light at a very specific wavelength. If I know that, and I know, for example, what the molar absorption coefficient is, I can determine the concentration of that complex in my sample and the concentration of the metal cation by working backwards from there. Now let's talk a little bit about the transition metal oxalate compounds we'll actually synthesize in this experiment. We'll be working with 3 transition metals. You'll choose one of the 3, iron 3+, copper 2+, and cobalt 2+, and the oxalate ligand is an organic ligand containing carbon and oxygen atoms that sort of looks like 2 carbon dioxide molecules smushed together with 2 extra electrons. The oxalate molecule has a net charge of -2, and so it has, in theory, 2 binding points. Each of those negatively charged oxygens could act as a binding point for a metal center, and in fact, it can be bidentate, meaning 2 binding points, or even tetradentate with 4 binding points, and we'll see that in one of the complexes in this experiment. So let's get into the structures of the complexes themselves, starting with the iron complex. So the iron 3+ is at the center, and it's surrounded by 6 oxalate ligands in an octahedral geometry. The net charge of the complex is -3, and this is because the iron has a charge of +3, and each of the oxalate ligands has a charge of -2, for an overall charge of -3 with the 3 oxalate ligands. This is counterbalanced by 3 potassium cations, which are the counter ions, and the compound also includes 3 waters, which are waters of hydration. So the overall formula is K3FeC2O43.3H2O. And it's important to keep that overall formula in mind when you're trying to calculate the weight or mass percent of oxalate within this compound. The copper complex is similar, but only has 2 oxalate ligands and 2 waters in axial positions above and below the equatorial plane formed by the oxalate ligands. So the geometry at copper is again octahedral, and the net charge on the complex is again anionic because of the 2 oxalate ligands, both with a charge of -2, and the central copper ion with a charge of +2. This -2 charge is counterbalanced by the positive charge of 2 potassium counterions, and there are no waters of hydration in this compound. Notice, however, that there are waters, but the waters are written inside brackets in the formula because there's a difference between the waters in the copper complex, which are actually coordinated to the copper, and the waters in the iron compound, which are waters of hydration likely associated with the potassium cations, but not directly coordinated to iron. So the difference in notation corresponds to a key structural difference between the waters in these 2 complexes. The cobalt complex is interesting because, like the copper complex, it has 2 oxalates coordinated to each cobalt, but each oxalate ligand is bridging 2 cobalt centers. And so I'm drawing that here with squiggly lines on either side to show that the other side of the oxalate ligand is bound to another cobalt atom. There's still 1 oxalate ligand per cobalt atom, but these are arranged in kind of an infinite chain of alternating cobalt and oxalate ligands. Notice also that the binding pattern of the oxalate is a little bit different, with the 2 oxygens bound to a common carbon atom binding to a single cobalt in this compound. So the overall formula is CO, C2O4, H2O2, and the H2Os are again written inside the brackets because the water ligands are coordinated to cobalt directly. And the most interesting thing to me about this structure is that it's polymeric. The cobalt centers and oxalate ligands form an infinite chain of repeating units, or a polymer. And now that we've seen these structures, let's talk a little bit about how we're actually going to synthesize these compounds in the laboratory. To begin thinking about how we're actually going to make these transition metal oxalate compounds, I want to go all the way back to our general reaction for the synthesis of a coordination complex. Ma plus Nl goes to MlN A+. And of course here typically we have counter ions to counterbalance that positive charge. Here they're anions. Now the way we typically accomplish this is we mix a metal salt with the ligand, and the counter ion in the metal salt is a relatively weak ligand with respect to the metal. So it might be something like a chloride, a nitrate, a sulfate, the conjugate base of the strong acids that we're used to seeing from the acids and bases unit. These things are easily replaced by stronger Lewis bases. And so we can think of the process of synthesizing a coordination compound in general as a ligand replacement process, where we're replacing a ligand that is a weak Lewis base with a ligand that is a stronger Lewis base. To begin getting into specifics, let's look at the iron synthesis specifically. So that's going to involve the use of iron trichloride hexahydrate. The chlorides are these weak ligands that we're going to replace. That's mixed with potassium oxalate monohydrate, and 3 equivalents of the potassium oxalate react with 1 equivalent of the iron trichloride to give our target coordination compound, as well as potassium chloride, 3 equivalents as a byproduct, and 6 waters as a byproduct. Now, this looks like a lot. It's a lot to sort through. But if we strip away all of the things that are spectator ions or just waters of hydration, we'll get to the essence of the synthesis of the coordination complex in this reaction, which involves Fe3+ as a Lewis acid, the oxalate anion as a Lewis base, specifically 3 of those. Those get together in a Lewis acid-base process to form FeC2O43, 2-, the coordination complex within the bigger compound. So how do we actually accomplish this? Well, both of the reactants are solids in their pure form. And so we're going to start with essentially 2 piles of solid. One is our iron trichloride hexahydrate, and the other is the potassium oxalate monohydrate. We're going to dissolve each of these in some water, and this will typically take some heating. We're going to want to heat things up to get the reaction going and get the reaction rate as high as possible. Once we have those solutions, and they're relatively hot, we're going to mix them at high temperature. That mixing will cause this Lewis acid-base ligand replacement process to take place very quickly, and as we cool the solution using an ice bath, we may observe crystals of the product form in the bottom of the reaction beaker. Essentially, the product precipitates. Now, this can be a little bit difficult. If you're having trouble with the precipitation or crystallization process, the protocol offers some tips on how to promote crystallization, either by adding a seed crystal or by adding ethanol to the reaction mixture in which the product is insoluble. After we have that heterogeneous mixture of our solid product and the liquid solution containing potassium chloride and any excess of the reactants that's unreacted, we need to separate out that pure solid coordination compound product, and we do that through vacuum filtration. After vacuum filtering and pulling air through the solid to allow it to dry, we will, in theory, be left with our pure product, which is the iron oxalate compound. Notice also that this filtration process separates the K+ and Cl- ions that are dissolved in the liquid. And so we're essentially going to throw that filtrate away because it has nothing of interest to us. What we're interested in with this synthesis is essentially how well we did relative to theoretical expectations. And we quantify that using what's called the percent yield. How much did we get relative to our expectation based on the amounts of reactants we used? This calculation hinges on which of the 2 reactants, way back when we weighed out the solids, is the limiting reactant. So you'll need to figure that out based on the amounts that you weighed and the stoichiometry of the reaction, the 1 to 3 stoichiometry that's shown here. To quantify the purity of your sample, we're going to use redox titration of the oxalate inside the sample with permanganate. We'll talk about that in a separate video.